Section 3, the respiratory system. Respiration involves external respiration and internal respiration. External respiration is the exchange of gases between the atmosphere and the blood. This occurs in the lungs. And internal respiration is the exchange of gases between the blood and the cells of the body. This happens at different places all over the body. So external respiration, internal respiration.
Lung cancer is the leading cause of cancer deaths in Malaysia for both men and women. Your lungs are two spongy organs in your chest. The left lung is divided into two lobes, or sections, and the right lung has 3 lobes. When you breathe in, air enters your nose or mouth and passes into your trachea, or windpipe. At the carina, the trachea divides into 2 bronchi, then branches into smaller bronchioles. The bronchioles end in tiny air sacs, or alveoli. Here, the oxygen in the air you inhale passes into the bloodstream, and carbon dioxide from your body passes out of the bloodstream. The carbon dioxide is expelled from your body when you exhale. Your lungs are encased by pleura, a thin membrane that protects them and helps them slide back and forth as you breathe in and out. Underneath your lungs is the diaphragm, a smooth, thin muscle that helps your lungs expand and contract as you breathe. Your lungs are connected to small collections of immune system cells called lymph nodes by way of lymphatic vessels. You have groups of these lymph nodes near your lungs, above your collarbones, and behind your breastbone, as well as in other parts of your body. The lymphatic vessels carry bacteria, cancer cells, and other unhealthy material away from your lungs and other organs in a clear fluid called lymph. Lymph nodes filter this material out of the lymph. Lung cancers most commonly start in the bronchi, but they can also begin in the trachea, bronchioles, or alveoli.
Okay, so the main organ of the respiratory system is the lungs. This is the site of gas exchange between the atmosphere and the blood, or external respiration. Your 2 lungs are divided into what are called lobes. Your right lung, which you see on the left-hand side here, is divided into 3 lobes, and the left lung has 2 lobes. Your lungs are located in the thoracic cavity, and they are surrounded by the rib cage on the sides and the diaphragm on the bottom. They're also surrounded by membranes called pleura. Remember I said in previous videos that you have epithelium, which is cells that line both the inside and outside of the body. And when we studied the skeletal system, I talked about periosteum. In the heart, you have the pericardium. These are all examples of epithelial tissue, or in this case, endothelial tissue, because it's on the inside of your body. The pleura is also endothelial tissue. They secrete a slippery fluid, much like the pericardium of the heart, and that decreases friction as the lungs expand, just like the pericardium reduces friction based on the heartbeat. So external respiration begins at the nose and the mouth. Air is filtered through the small hairs that you have in your nose. The air passes into the nasal cavity above the roof of the mouth. So here we have what's called the hard palate. If you take, this is your tongue, by the way. And yes, this is a real human being that's been like cut in half. So if you take your tongue and you touch the roof of your mouth, that's the hard palate. Now, if you move your tongue a little bit towards the back, you'll feel when it becomes soft. That's usually back here. That's called the soft palate. So this is your nasal cavity. You can see here There's mucous membranes. That's like why it looks kind of shiny. And when you are sick and you can get your, this is your sinuses, I think, and your sinuses get full of phlegm. And that's when you feel like lots of pressure because of course your eyeballs are just above there. So mucous membranes, which you can see here, maybe I'll stop using the marker. I'll use, so these are mucous membranes. They warm and moisten the air, and your entire respiratory tract is lined with mucous membranes because the air that goes into your lungs has to be warm and moist. This prevents damage to the delicate tissues in your respiratory system. And of course, the walls of your respiratory system are lined with cilia. If you remember way back when, cilia are the short hair-like extensions of cells. This helps to trap particles that are inhaled. If you do inhale like dust or dirt particles, the cilia and the mucous membranes in your respiratory tract will trap them. And then you'll cough. When you cough, it goes up to your throat again, and then you'll swallow it. So based on, this is something called the epiglottis. And I'm just going to talk about it now since this is a really good picture to look at. So this right here is your trachea. That is the air tube that leads from your mouth and nose down to your lungs. What you see behind here, that's your esophagus. That goes from the top of your throat down to your stomach. So when you swallow, your tongue pushes back and down on the epiglottis so that it then covers the trachea to prevent any food or liquid from entering your trachea, which leads again to the lungs. And it makes sure that food and liquids go straight down your esophagus so that you don't choke. Now, the moistened filtered air moves to the pharynx, which is the back of the nasal cavities and the mouth. It's just this kind of open area back here where you find the passageway for both the food down the esophagus. Like I said, the esophagus is in the back. The trachea is in the front. You can feel your trachea if you if you feel in the front, you're feeling your trachea, and I'll talk more about that in a minute. So again, when food is swallowed, the epiglottis, epi means on and glottis means tongue. So it literally means like on the tongue. It's a flap of cartilage which pushes down and covers your trachea so that food and water don't go into your lungs. This is the cilia that I was talking about. So that's what the epithelium in your respiratory tract looks like. These are cilia, short little hairs. It's also covered in mucus, which helps to trap particles. Now, at the upper end of the trachea is something called the larynx. The larynx is basically your vocal cords, because if you look here, this is like a top-down view into the top of somebody's throat. And you see here, that's where it's located, right at the top of the trachea. There are two ligaments that are stretched across the larynx. So as air pushes past those two vocal cords, they vibrate just like a guitar string. If you pluck the guitar string, it makes a sound. Now, if anybody plays guitar or piano or any stringed instrument, and you understand how pitch works, the tighter the strings are pulled, the higher the pitch is. So on a guitar, the bottom strings are the looser strings, they're also thicker, so they produce a lower pitch. And the top strings are stretched tighter, so they make a higher pitch. And the same thing is with your vocal cords. When you want to speak low and you want to talk like this, then that means your ligaments are less stretched, they're more relaxed. But when you want to talk like really high and have a high pitch, then your vocal cords or your larynx or the ligaments are going to be pulled tighter. And then volume just depends on how much air is being pushed back. So if you whisper, there's very little air going past. But if you talk really loud, that means that there's a lot of volume there's a lot of volume of air, a lot of air being pushed past.
Now give me a singing. At a low pitch and then sing up. And now high to low.
I'm trying to circle there. There we go. That's one. Those are the vocal cords. Okay, not the white things that you. Oops, it looks different on my screen. The two white. No. There. This two white things you see here. Those are not the vocal cords. It's the ones on the sides. This is really cool.
Beatboxing existed in the Dark Ages, I'm sure many of us would have found ourselves tied to a fiery pyre to be burnt alive alongside our godless peers. You see, for the uninitiated, the act of conjuring up otherworldly sounds from the dangling depths of our throat seems like the audible equivalent of witchcraft. However, many practitioners of this sonic sorcery, like myself, know that buried below the smoke and mirrors of the microphone is a world of techniques and uncanny precision that allows us to exist as the freaks we are today. So, in this series, with the help of a crack team of specialists, I would like to peel back the layers of my face and welcome you inside the mouth, the mind, and the mechanics of the beatboxer. The question that I get asked a lot is, how the are you making those noises? I decided to find out. So we paid a visit to a man with an impressive amount of letters after his name who happens to know the back of your throat like the back of his hand. Welcome to my larynx, Dr. Broadhurst.
Right, so there's two cameras that I use. The first is a flexible one, and that's 5 millimeters in diameter. That'll go through the nose, past the tonsils, down to the larynx. Right. And through that, on a large monitor, we'll be able to see all the movements, the actions, the activities of what goes on, not just in the larynx, but up in the base of the mouth, base of the tongue, and see how all that creates different sound. And then the second part of it's a rigid camera. It's about this long, and it'll go through the mouth. And it's a little like sword swallowing. It'll go down, but it's got a much higher resolution camera in it. Right. So it'll give a much clearer picture of what tissue is vibrating to make the sound that it does.
All right, cool. Well, maybe we should start by putting some things in my face.
Sounds good.
Warning, this video contains very graphic images from the depths of my throat. Stop eating now. You may vomit.
Yes, delicious.
What they were doing just there was spraying an anesthetic or a numbing agent in the back of his nose and the back of his throat so that he doesn't gag on the endoscope or the camera that they're going to insert into his throat.
So you put your tongue straight out of me. Just breathe through the mouth. Just try to say now go. So the vocal cords look good. Nothing weird or abnormal or unusual. This is the flexible one. Now the only thing we don't know is how much having a camera in the nose is going to interfere with it. I guess you'll find out. Yeah. This is the other little microphone. We need that sort of near you. There's a lot of space up there. Yeah. I'm sure you can feel. Oh yeah. Oh yeah. Yeah. So this is the back of the what's called the nasopharynx. Wow. And what you see coming up there, just go cut, 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 cut.
I'm judging by everybody's reactions right now. It's looking pretty weird.
So that's the soft palate closing up against the nasopharynx. So you can imagine if you have a palate or problems back there, that you wouldn't be able to close and make all that sound.
Yeah.
So now we see the larynx. This is the bit where it might be difficult for
See
you.
here, oh,
Now what we're going to do is just watch.
that was one vocal
See
sound.
what happens. Yeah, whatever you want to do.
These two on the sides.
Have a swallow for me there.
Too much saliva.
Certainly in there, isn't it?
Yeah.
I think it sounds okay. I can feel it in there.
So give you a break this moment. Most of what I can see from where the camera tip is placed is it's sitting right at the top of the soft palate. So you can imagine the tongue sitting here. The sound that you use to generate a lot of it is all the movements of the tongue. Whether it's flat forward, it's lifted up, it's pushed back, it's flattened out across the back. There's a huge range of shapes, which is what creates all those sounds. When you look further down, you can see the larynx complex either squeezing like crazy for specific sounds or pulling right up towards the back of the nose. And then you'll see other tissues around vibrating, which are also making sound.
Well, should we have a look at some of the footage?
Yeah, let's do it.
Today, I gained some valuable insight into the contents of my throat and almost the contents of my stomach. But all jokes aside, my journey deep into the laryngeal abyss was certainly eye-opening. In 2 generous hours under Dr. Broadhurst's endoscope, I found out more about the complexities of my throat and its noise-producing mechanisms than I could have ever hoped to achieve with self-exploration and 15 years of a questionable career choice. So thank you for simultaneously opening my mouth and my mind to what's behind my world of weird noises. Catch you all in the next invasive episode of Live.
Okay, so then that's how we produce sound using our larynx. Okay, so the trachea, which is the tube that leads from the pharynx, which is the back of the throat, to the lungs, branches off into 2 bronchi. Bronchi is plural, bronchus is singular. Each bronchus leads to a lung. The walls of the bronchi are made of smooth muscle and cartilage, and of course they're lined with cilia and mucus, like the entire respiratory tract is. In the lungs, so if I can outline the lungs for you, let's do it in blue. Hello, here we go. So that would be the lungs. Inside the lungs, the bronchi branch into smaller and smaller tubes. And of course, we add the eoles at the end, just like we did in the arteries, arterioles. The bronchi branch into arterioles. And then finally, the bronchioles end in these tiny little clusters of air sacs called alveoli that should be highlighted because it is a vocabulary word. And there's a network of capillaries surrounding each alveolus. Again, alveoli plural, alveolus singular. Each lung contains 300 million alveoli, and the total surface area is 70 square meters, which is 40 times more surface area than your skin. That is in each lung.
When you breathe, air travels through your nose, down the trachea, and into smaller and smaller airways called bronchi. These bronchi branch into smaller passages called bronchioles, and finally into small, thin, fragile sacs called alveoli. During inspiration, the alveoli in the lungs are filled with air. It is here that oxygen is exchanged for carbon dioxide. Blood cells absorb oxygen from the capillaries in the alveoli. As carbon dioxide, waste product is released back into the lungs from the veins. During expiration, the carbon dioxide is expelled from the body. Oxygen-rich blood then travels to the heart so it can be pumped back to the body where it is needed.
Okay. In the lungs, gases are exchanged between the alveoli and the blood and the capillaries. That's that's external respiration. Oxygen needs to be transported throughout the body. Oxygen to be transported throughout the body moves into the bloodstream, and carbon dioxide to be eliminated from the body moves into the alveoli. Whew, that was rough getting through that. Okay, so how does gas exchange occur in the lungs? When air moves into the lungs, the oxygen in the air moves across the alveolar membranes and then the capillary membranes. Carbon dioxide is going to move in the opposite direction according to the concentration gradient. So if, let's say I've got, here's an alveolus. So this is inside the lungs. This is the bloodstream. And this is inside the lungs. So inside the lungs, I have a high concentration of oxygen and a low concentration of CO2. In the bloodstream, wow, that's bright in my eyes. In the bloodstream, we have a high concentration of carbon dioxide and a low concentration of oxygen. That means that oxygen is going to move from high to low. So it moves out. And carbon dioxide is also going to move from high to low. It's going to go from the blood to the lungs. Oxygen goes from the lungs to the blood. So the air moving in is rich in oxygen. The blood in the capillaries has low levels of oxygen and high levels of O2, just like here. The difference in concentration causes the diffusion of the two gases, like I just illustrated. Now, how does the oxygen and the carbon dioxide move in the blood? Like, how does it physically get transported? 97% of the oxygen moves into red blood cells where it combines with hemoglobin. Remember, hemoglobin is composed of 4 polypeptide chains. Each polypeptide chain contains 1 iron atom. So each hemoglobin has 4 iron atoms, and each iron can bond to 1 oxygen molecule. When the oxygenated blood reaches the cells, the concentration is higher in the blood than the surrounding cells. So again, if we have a capillary here, and so this is tissue, and of course this is a capillary. So in the tissue, we have a high concentration of CO2 and a low concentration of O2. Inside the capillary, we have a high concentration of O2 because we just transported the oxygen from the lungs, and we have a low concentration of CO2. So again, we exchange high to low. It all happens by diffusion.
The alveoli are the site of gas exchange in the lungs, and they're located here at the very end of the bronchioles. They have a structure that's something like this, We often describe it as having a sort of cauliflower shape, but basically they're just tiny little air sacs at the end of the bronchioles. If we see it here represented in more of a diagram format, we can see what's going on. First of all, oxygen and carbon dioxide are constantly being supplied and removed through breathing. Let's look a little bit closer at the lining here. Notice that it's only 1 cell thick. Oxygen can diffuse across the cell membrane of the cell that lines the alveolus. From there, it can obviously diffuse across to outside of that cell. The same thing applies for the lining of the blood capillary until eventually it diffuses into the red blood cell where it can bind with hemoglobin to form oxyhemoglobin. Similarly, carbon dioxide can also diffuse across these cell membranes and reach the alveolar sac to then exit the body. Now then, oxygen, as we've already said, is constantly being supplied through breathing, but it's also being taken away from this area because of the blood flow. What this means is that we are constantly maintaining a concentration gradient, which is what allows this transfer of gas, this gas exchange, to continue. There are some important features of the gas exchange surface that you need to know. First of all, it's got a large surface area, which is provided by this particular shape of the alveoli, and also by the fact that there are lots and lots and lots of them inside of the lungs. It's very thin, which provides a short diffusion pathway. Notice that the lining is only 1 cell thick. It's also got a moist lining. The inside of each alveolus sac is moist, which allows gases to dissolve, which then allows them to diffuse across the lining. It's got a very good blood supply. Each one of the alveoli has lots and lots of blood capillaries surrounding it. If we have a little look at what lung tissue looks like under a microscope, we can see this sort of zigzag, crisscross sort of mesh of little almost streams. This is the capillary network, and we can tell that because if we look at one of these individual little red splotches here, those are individual red blood cells. Finally, there is very good ventilation, and that basically just means there's a really good supply of air, which is supplied through breathing. A little bit of exam help on this. You might get asked to describe the features of the lungs that make gas exchange efficient. Well, the exchange surface has a large surface area, and that's provided by the large number of alveoli, and the surface is only 1 cell thick. Remember that provides a very short diffusion pathway. And it is supplied with blood by a very dense capillary network. So there, you're easily going to get those 3 marks.
Okay. So carbon dioxide is transported a lot more differently than oxygen. Only 8% of CO2 dissolves in the plasma. Remember, the plasma is the liquid portion of the blood. 25% of it binds to hemoglobin, but the other 67% is going to react with water in the plasma to form carbonic acid. Then the carbonic acid is going to dissociate into bicarbonate ions and a proton. So what does that look like? We have CO2 is going to dissolve in the water to form carbonic acid, which is H2CO3, that's aqueous. This is then going to break down into bicarbonate ions, which is HCO3 minus 1, and a proton, which is a hydrogen ion. So this is the form that most of the carbon dioxide gets transported in the blood. When it reaches the lungs, the reactions are reversed. So that means that these two combine together to form carbonic acid, which then dissociates into CO2 and H2O in the lungs. So now that we know how gas exchange occurs and how the two gases are transported in the blood, it's time to learn about the mechanisms of breathing, how it actually physically works. Breathing is the process of moving air into and out of the lungs. Inspiration is taking air into the lungs or breathing in. When you take a breath, your chest expands as the muscles contract to move your ribs up and out. At the same time, the diaphragm flattens and pushes down. So this increases the volume of the thoracic cavity. Now, because I just uploaded the video on Boyle's Law, we apply Boyle's Law to this process. So if we increase volume of the chest, so the chest expands, which means your sternum and your ribs are lifted up and outwards. Your diaphragm contracts, which means it pushes down. All of that increases the volume inside your lungs. So from Boyle's Law, we know that if volume goes up, pressure is decreased. So inside your lungs, pressure is decreased. Compared to outside, it has a higher pressure, so therefore air moves into your lungs. Expiration is releasing air from the lungs. So your ribs relax. So you can see that they're more down. Your diaphragm relaxes, which means that it is more in a U shape. When your diaphragm contracts, it flattens like this. Relaxed, it moves back up, which means inside your lungs, you have decreased, oops, that's not a good color, black. You have decreased the volume, which means you have increased the pressure, so air is forced out. Again, Boyle's Law, relating it to how you breathe, which is kind of an important thing. Okay, so how is our breathing regulated? It is, of course, controlled by your brain. Your brain and your brain stem, which is at the base of your brain, monitors the concentration of carbon dioxide in your blood. When you have a higher activity, that means that your muscle cells are producing more carbon dioxide. And so that's going to stimulate nerve cells in your brain. That then in turn causes your brainstem to trigger your diaphragm to both increase the rate that it contracts and relaxes, but also the depth, so that you start breathing in not just faster, but deeper as well. All of this happens subconsciously. So if you think, I'm going to commit suicide by holding my breath, that doesn't work, because your brain automatically is there for self-preservation. So if you hold your breath as long as you can, usually even before you pass out, you can't help it. Your brain will make your diaphragm contract, which then forces air into your lungs. But let's say you can hold your breath long enough for you to pass out. That means that your brain is like, okay, fine, this idiot is still not breathing, so we're just going to make him go to sleep now, so that the brain takes over and then normal breathing continues. So one of the things that kind of irritates me about the movies when somebody strangles someone else is that you see them strangle them until the person passes out and then they stop strangling. But I'm like, if that person's passed out, they're not dead yet, they just passed out. So you'd have to strangle them for longer afterwards. Not that that means that, I'm not giving advice or anything, just that irritates me about movies. Last thing, this is what lung cancer does to your lungs. Of course, smoking is one of the leading causes of lung cancer. You can see how the lung loses its elasticity. That is something called emphysema. When the lungs cannot stretch as much, so you can't get as deep of a breath. And of course, you've got the tar, which is the black stuff on top of it. And like I said, emphysema, this is where the alveoli lose their elasticity, which is their ability to stretch. So you end up usually having to be on oxygen. So you carry a little oxygen tank around with you at that point.